Hello everyone, my name is Dave Bass and I am a Principal Field Application Scientist with PerkinElmer and I'm very excited to present to you today. In today's talk, I will discuss the Stabilized Temperature Platform Furnace concept, also known as STPF, and the various components that comprise this technique in detail to provide a more complete, rugged, and systematic approach for graphite furnace analysis. Let's start by briefly reviewing the atomic absorption techniques of flame and furnace. Comparing in terms of basic spectrometer design, the components are essentially the same, but now we replace the burner head with a graphite tube as a sample cell. Flame AA is fast, produces sub-ppm levels of detection, has well-documented interferences, and requires milliliter volumes for determination. Graphite furnace AA, with its multi-step program, is slower than flame, is a total consumption discrete injection technique that only requires microliters of sample, attempts to control interferences by incorporating the STPF concept, and typically produces sub-ppb detection limits. For example, the analysis of lead in blood to assess exposure in pediatric patients historically became quite popular by graphite furnace due to its accuracy at ppb levels and the requirement for a minute amount of sample, which is often limited here. Let's take a more focused look at the detection limit capability, with particular emphasis on graphite furnace, the focus of today's talk. Notice that graphite furnace is the closest technique to ICP-MS detection limits, so that before ICP-MS technology received analytical approval from the various regulatory agencies and design improvements lowered the initial cost of investment over time, a graphite furnace and an optical ICP were very complementary techniques and often seen in most laboratories. It is also important to note that, although not the focus for today's discussion, hydride generation AA, in concert with EDL lamps, was also considered due to its comparable detection limit capability as well. Let's begin with a couple of definitions to start with regarding actual furnace design. The HGA or heated graphite atomizer was first and utilizes either continuum source background correction or transverse Zeeman. THGA or transversely heated graphite atomizer incorporates longitudinal Zeeman and, as we will see, provided a significant enhancement to graphite furnace analysis. For each, please note the various instrument models associated with each design historically, up to the Pinnacle series, our current AA platform. Before we begin to discuss how the STPF concept is incorporated analytically, we need to ensure that a sound scientific procedure has been developed and implemented on a routine basis to create consistent performance. Items such as cleaning the contact cylinders to maintain consistent heating of the tube and removing a potential source of background and vapor phase interferences. Properly conditioning a new graphite tube with the provided software program to seal the pyrolytic coating and ensure expected tube performance. Aligning the autosampler tip to verify proper sample delivery without touching the tube platform or seeing splattering. And verify sample drying using the tube camera and dental mirror during the initial steps of the furnace program. There are a number of undesirable effects associated with poor drying, such as degraded tube life, poor precision, loss of sensitivity, and compromised data quality. Remember, the default drying steps are based on a slightly acidified aqueous matrix based on injection volumes of 20 microliters of solution and 5 microliters of matrix modifier if recommended. Even with a typical water sample, drying must be verified, and especially if a potential matrix involves a change in dissolved solids, surface tension, viscosity, or elevated acid content. There are default programs available that include the recommended wavelength and slit, temperatures for charring and atomization, sensitivity, approximate linear range, and the type and amount of matrix modifier, designed to provide a reasonable starting point for the analyst. Next, we proceed to the three blanks, Then confirm the accuracy of a standard and verify adequate lamp performance by checking the sensitivity and calculating the characteristic mass value. I cannot stress the importance and value associated with investing the time to work through this process consistently and systematically. Why is performing each of these blanks so important? The spectrometer blank, initiated by taking a read via the Syngistix software without injection or running the furnace program, establishes the electronic baseline, taking into account the system components such as optics and lamp. Even though we always quantitate in peak area, you can look at the amplitude of the signal via the peak height to gain insight as to the inherent noise level. The furnace blank, by initiating the program without injection, will provide insight into proper furnace alignment and determine if the signal is adversely affected by black body radiation, and provide verification that analyte is not present in the furnace by the absence of a discernible peak. Ideally, the furnace blank will closely mimic the spectrometer blank, but in cases where a peak is observed, additional firings are necessary to determine if the peak is reduced with subsequent attempts. The calibration blank, matched to the acid content of the standards at a minimum, injected along with the matrix modifier, will provide insight as to the inherent analyte contained within the reagents, and that potentially added from associated components such as pipette tips and volumetric flasks used in the overall preparation process. This is why we recommend the use of trace metal grade acid, high purity modifier solutions, clean volumetric plasticware, and a quality source of DI water. Since the peak area absorbance generated by the calibration blank is subtracted from every solution, it is imperative to run more than one blank to establish a reproducible signal. Additionally, the use of lower grade acids or reagents producing extremely high blanks will invalidate the calibration and produce inaccurate data. Note the information located in the performance check section of recommended conditions. The sensitivity check is the approximate peak area expected for a 20 microliter injection at the indicated ppb concentration using recommended conditions. In the example above, a 20 microliter injection of lead with default modifier should produce an approximate signal of 0.15 peak area. The definition and mathematical calculation of the characteristic concentration is indicated above. Based on the resultant blank-corrected absorbance, this will tell the analyst if the absorbance is acceptable based on that characteristic mass value. Here is a screen capture in the Syngistix software showing where the characteristic mass icon itself is located, and an example of the actual window. Here we see a calculated characteristic mass value of 29.9 based on the prepared 50 ppb standard with a reference or comparison value of 30. What is considered the acceptable range for the characteristic mass? As we can see, the target range is 20% of the comparison value. If within, no additional action is required on the part of the analyst. Since the peak area absorbance is in the denominator of the equation, a high value would result from the standard producing a low absorbance. There could be many causes for this: poor artisample or pipette delivery, aging or an improper lamp, condition of the graphite tube and/or contact zoners, etc. During method development, it may be necessary to make significant changes to the default method to create an optimized program. Now that we've discussed some considerations for setup and optimization, let's move on to the stabilized temperature platform concept. In reality, this evolved over several years of development. As you can see, the list includes the use of pyrolytically coated graphite with platform atomization, rapid furnace heating profiles, gas stop during the atomization step, incorporation of matrix modification when indicated, peak area quantitation with BOC, and background correction applied. We will now look at each of these in greater detail. Even though we start with high purity graphite as the base substrate, the surface of carbon is irregular, and it was discovered that applying multiple layers of high purity graphite pyrolytically provides a more consistent platform surface and eliminates the potential binding sites where analyte can be trapped upon interaction with the tube during the furnace program. Properly sealing this pyrolytic coating when inserting a new tube is extremely important, and why we add a built-in tube conditioning program to the software for convenience. When we view the development of platform technology from a historical perspective, we start with the insertable evolved platform on an HGA designed furnace. At that time, there were grooved tubes with separate platforms that were placed into the tube using an insertion device. Since the fit was not consistent and that some platforms fit tighter than others, we were able to determine this effect created a wider range of characteristic mass values when analyzing the more volatile elements that require a lower atomization temperature, such as lead, cadmium, or silver, with a tube-to-tube comparison. This was due to the degree of direct heating between the tube and platform based on the fit and its effect on the resultant sensitivity. Based on this information, it stands to reason an opportunity to improve the design might be available. As a result, we developed the integrated platform tube that is manufactured from a pyrolytically coated single piece of graphite. Not only does this provide convenience to the analyst, as there's no longer a platform to insert, but more importantly, produces the true platform effect as it is only attached at one point and therefore is totally indirectly heated and produces more consistent characteristic mass values from a tube-to-tube basis from volatile to the more refractory elements. What about advances in the actual design of the furnace itself? Notice the effect of the temperature distribution in the newer THGA design, which creates a more consistent isothermal condition along the entire tube length by heating across the tube compared to the temperature gradient associated with the original HGA design. This elimination of the temperature gradient and cool end phenomena reduces carryover, since the analyte can no longer naturally migrate to the cooler ends and devolatilize, and reduces the possibility of the occurrence of vapor phase or non-spectral interferences that can adversely affect data quality as well. For the THGA designed furnace, there are two types of tubes available, the open or standard tube and the end cap tube. Both of these incorporate the integrated platform design, but the addition of the graphite inserts with the end capped version create a greater resonance time of the ground state atoms in the light beam, improving sensitivity and signal to noise. Because the integrated platform is the same, there is no need to adjust the furnace program to incorporate the different tube. The characteristic mass values for each applicable element with the end cap tube are provided in the recommended conditions of the Syngistix software as well. Here we see the sensitivity enhancement for a variety of elements from volatile to refractory. Notice there is an improvement across the board except for vanadium, which is classified as a hard refractory element that will form stable oxides or carbides in the graphite tube. There would be no advantage to the use of an end cap tube for these types of elements, such as barium, vanadium, titanium, or boron, since there is no significant improvement in signal to noise, and the greater surface area of carbon associated with the end cap will produce more unwanted carbides, creating greater carryover issues. When the sample is placed on a Laval platform, the sample experiences the temperature of the platform, not the temperature of the tube wall. Since the platform is by design in poor physical contact with the round tube surface, the platform is heated primarily by radiant rather than conductive energy. This means that the platform will heat more slowly than the outer tube. During the rapid heating in the atomization step, when the platform does finally reach the atomization temperature for the analyte, atoms are released into a furnace environment, the temperature of which is similar to that of the platform. Since the platform is heated by radiation from the walls of the tube, the temperature of the sample on the platform is delayed relative to the wall of the tube and therefore to the vapor within the tube. Instead of volatilizing the analyte as the temperature is changing as massive gas expansion is occurring, we delay the appearance of the ground state atom cloud when the gas phase has reached a more stable or steady state condition. Here's a comparison of atomization profiles using the insertable captured platform versus the newer integrated design. We can clearly see the desired effect of increased temporal separation of heating between the tube and platform associated with the integrated design, delaying the appearance of the ground state atom cloud past the point of initial gas expansion during atomization, and notice the increased heating rate also associated. Next, we will reinforce this concept with a discussion of the effect of rapid furnace heating. Since faster heating rates will produce a denser atom cloud, this will also produce greater sensitivity. In our instruments, the max power heating rate is 2000 degrees per second and must be controlled by the use of an optical sensor to ensure the maximum temperature is not exceeded. We always recommend max power heating for STPF conditions, and is implemented by using a 0-second ramp during the atomization step. For this reason, all default furnace programs are reflective of the concept of max power heating. By increasing the temperature of the furnace at the maximum possible rate during atomization, the tube wall and surrounding argon are heated much faster than the platform, thus ensuring a stabilized tube temperature at the time of analyte volatilization, as shown above. This helps to ensure that this desirable, stable condition will be established before the release of even the most volatile analyte forms. The release of analyte atoms into the same furnace environment for all analyte forms is the prerequisite for elimination of non-spectral interferences. To produce the fastest possible heating rate, the full or maximum power capabilities of the furnace power supply are applied to the graphite tube at the beginning of the atomization step. If this power level were to be applied continually, the final temperature would reach levels which would virtually destroy the graphite tube. Therefore, the application of maximum power is reduced to the level required to hold the selected atomization temperature whenever that temperature is reached, and is precisely controlled by an optical temperature sensor, which sends a signal to the furnace power supply whenever the preset tube temperature is reached. Another way to evaluate the effect of the heating rate is by examination of the acquired sensitivity. There are two very important points to mention here. One is that we don't ever reach maximum sensitivity with the normal heating rate, meaning we haven't achieved full conversion of the analyte into the ground state, and two, the required temperature is significantly higher compared to the max power heating rate, resulting in degraded tube life and the possibility of increasing background and vapor phase interferences that could compromise data quality. In order for atomic absorption to occur, ground state atoms free from recombination or other vapor phase interferences need to be produced in the spectrometer light path, and the creation of an isothermal tube condition, atomized from the platform, at the max power heating rate all work in concert to produce desired analytical effect, shifting the equilibrium in the proper direction. Now, let's move on to the topic of matrix modification. In most cases, the modifiers indicated in our recommended conditions are thermal stabilizers: palladium with magnesium nitrate, ammonium dihydrogen phosphate by itself, or ammonium dihydrogen phosphate in combination with magnesium nitrate would be typical examples. To the left, you can see the stock solutions currently offered by PerkinElmer. It is customary for the analyst to prepare a working mixed modifier solution from the stock bottles. The importance and benefit of reducing analyte volatility cannot be overstated, since it allows us to char at the highest possible temperature while removing as much of the unwanted matrix components as possible, which will typically produce lower background and fewer vapor phase interferences. Modifiers can perform other functions such as matrix equalization, particularly when magnesium nitrate is used by itself, or to increase the volatility of the sample matrix, such as the use of ammonium nitrate in a sodium chloride solution. However, since the overwhelming majority of the time the modifier is acting as a thermal stabilizer, we're going to focus on that primarily. Let's investigate the impact of the charring temperature and the evolution of modifier selection over time. As you can see, the highest possible pyrolysis temperature is significantly increased in almost all cases with the modifier than without, which will potentially produce significantly lower levels of background during the atomization step. Also notice the use of nickel nitrate for elements such as arsenic and selenium. Although it worked quite well, the desire to then analyze for nickel became quite difficult due to the inherent contamination added with each solution from the modifier itself. In that case, nickel nitrate would not be considered an ideal modifier, since nickel could be an element that also needs to be analyzed. However, when switching to the combination of palladium and magnesium nitrate as a mixed modifier, you can readily see that it is applicable to a large number of elements, and considering that very few applications require the analysis of palladium, the contamination issue becomes significantly reduced. This applicability will be discussed later when we begin a discussion of EPA method 200.9. Let's now take a look more specifically at the charring profile for just selenium with and without modifier. Without the mixed modifier, any temperature greater than 400 degrees will result in premature loss of analyte and produce low bias data. Using the modifier now provides an increase in the pyrolysis temperature close to 1200 degrees due to the transformation of selenium to a more thermally stable form, which will typically result in lower background to contend with during atomization. Here is a pyrolysis study summary for lead using the various possible modifiers. Upon observation, there are four major conclusions to draw from the displayed data. First, we can see phosphate compared to phosphate with magnitrate produces essentially the same sensitivity. Why is that? Because the thermal stabilization is being provided from the phosphate. The second point is that although the sensitivities are the same, notice we gain some additional charring capability with the phosphate magnitrate combination. In this case, the magnesium nitrate is acting as a helper modifier, performing some matrix equalization in addition to the thermal stability provided from the phosphate. Our last 2 points are centered around a comparison of phosphate magnitrate to palladium magnitrate. We gain even greater charring capability with the palladium magnitrate as the lead has been transformed to an even more thermally stable form. And lastly, notice the sensitivity goes down with the combination of palladium and magnitrate. This is due to the atomization kinetics associated with palladium and magnesium nitrate, and that the formation of the ground state atoms creates a peak that tends to be taller and skinnier, where the peak area absorbance is smaller, producing a higher characteristic mass value. What would comprise an example, or I might choose one modifier over the other. In cases where the matrix is less complex, and we don't require or need the extra charring capability, phosphate or phosphate with magnitrate would be preferred. However, in more complex matrices, where high background is creating additional analytical issues, such as poor precision or unacceptable spike recovery data, and a higher pyrolysis temperature might be warranted, then the palladium magnesium nitrate would be the modifier of choice. For the purposes of clarity, here's an example of using a modifier to change the volatility of the matrix without doing anything to the analyte itself. Sodium chloride is a relatively non-volatile compound requiring high pyrolysis temperatures, which would result in the loss of many analytes. By adding ammonium nitrate, however, the simple matrix is now converted to more volatile components, which now could be driven off with high efficiency at considerably lower pyrolysis temperatures that enable us to keep the analyte intact. The combination of max power heating and the Laval platform goes a long way towards eliminating non-spectral or vapor phase interferences. However, one potential problem still exists. The rate at which atoms are released from the platform surface into the furnace environment will still be controlled by the sample matrix in which the analyte resides. Any measurement technique, which depends on atomization rate solely, such as peak height, would therefore show matrix effects if there is any difference in the rate of formation between samples and standards. In this example, even though the concentration of the blood sample is the same as a standard, with the same preparation using the same furnace program, the peak height is quite different, but the peak area is approximately the same. What is the analytical impact? Calibrating in peak height will produce a high bias in sample results, but peak area will provide very accurate results. The key point here is that if you are successfully able to completely transform the analyte to the ground state during the atomization step, it will not solely depend on the rate of formation, allowing the use of aqueous standards with more complex samples and still provide accurate results when using peak area quantitation. One complication with peak area measurement has been the significant effect of any baseline drift. Peak area is measured by summing all observed signals over the atomization time, which could vary from 3 to 8 seconds depending upon the element and its level of volatility. While current instrument electronics are very stable, the effect of even a slight baseline change becomes noticeable when summed over several seconds, considering a time elapse between the read step from one solution to the next. Automatic zero adjustments immediately prior to atomization could be used to compensate for such effect, and as a result, baseline offset correction, or commonly referred to as BOC, was developed. When BOC is in use, it measures the instrument baseline reading immediately prior to atomization. Each reading during the peak area integration is then automatically corrected for this baseline offset. This eliminates all drift effects and improves the accuracy of peak area measurement while also maintaining the correction for sample blanks implemented with the automatic zero adjustment. As you can see in the example above, the BOC time is 2 seconds, meaning it will occur exactly 2 seconds before atomization. If during the analysis an error message stating that the background BOC is changing is generated, there are 2 typical options to remedy this. One is to increase the BOC time to 3 or 4 seconds if you have an older lamp and believe the message is due to lamp instability. However, if this message is generated from a sample where there is still matrix being removed during the BOC measurement time, generating the error, the remedy is to add time to the pyrolysis step in 10-second increments to allow greater time for this process to occur before the BOC measurement actually takes place. From an analytical perspective, here is the real impact of not using BOC. As can be seen, a small baseline shift of only 0.001 absorbance integrated over a 5-second period produces a significant 5% error in the measurement, and therefore is a requirement for peak area quantitation to maintain a stable baseline throughout the run. Now, let's move the discussion to a topic of nonspecific absorption. Background absorption is a nonspecific attenuation of light at the analyte wavelength caused by matrix components in the sample. Unlike atomic absorption, background absorption can be broadband, sometimes covering tens or even hundreds of nanometers. This broadband absorption normally is due to molecular structure or light scattering caused by undissociated sample matrix components in the light path during the atomization step that will cause high bias results if not accounted for. There are two primary ways to correct for this in PerkinElmer instruments depending on the actual model. So both techniques, Continuum and Zeeman, will be discussed. Here we see what the typical instrument diagram entails when adding continuum correction, which involves measurement from a second source with its associated optics and electronics for measurement to correct for the background. During this process, the two lamps are observed by the detector alternately in time, and instrument electronics separate the signals and compare the absorbance from both sources. An absorbance will be displayed only where the absorbance of the two lamps differs. True atomic absorption, which absorbs the primary source emission and negligibly absorbs the broadband continuum source emission, is still measured and displayed as usual. In other words, we take the AABG measurement from the primary source lamp and subtract from it the BG measurement of the continuum source to result in background corrected AA. To provide a brief summary, there are some considerations associated with this correction technique from the fact that the background component of the absorption signal is measured from one source, while the total uncorrected signal is measured with another that has a totally different spectral resolution. This leads to the possibility of inaccurate compensation if the two sources do not view exactly the same portion of the atom cloud, especially at higher background levels, meaning source alignment is critical. The additional required components typically add some baseline noise as well. It is also important to match the energy reading in the inline lamps window as close as possible between the two sources. For very bright lamps greater than 300 nanometers in wavelength, where the intensity of the D2 lamp begins to diminish, it may be necessary to decrease the current of the primary source lamp in order to achieve an acceptable match. And finally, since the two sources are spectrally different, background absorption exhibiting fine spectral structure may attenuate the two sources at different degrees, leading to inaccuracies in background correction in these cases. This is one of the greatest limitations of continuum correction. However, all things considered, this correction technique does work quite well for simple and less complex matrices. Peter Zeeman was a Dutch physicist who first discovered the Zeeman effect, subsequently winning the Nobel Prize in Physics back in 1902 for this. By placing the poles of an electromagnet around the atomizer and making alternating absorption measurements with the magnet off and then magnet on, the uncorrected absorbance when the magnet is off and the background absorbance only when the magnet is on are measured. Zeeman background correction uses the principle that the electronic energy levels of an atom placed in a strong magnetic field are altered, thereby changing the atomic spectra, which are a measure of these energy levels. It is based on the fact that in a normal pattern, ground state atoms split into three components, two of which, the sigma components, slightly migrate from the analytical wavelength. The third component no longer absorbs when the Zeeman effect is applied longitudinally, meaning the only component remaining that can actually absorb light when the magnet is on would be background. The signal from each of the two cycles, meaning magnet on and magnet off, are observed by the detector alternately in time, and instrument electronics separate the signals and compare the absorbance from both cycles. And absorbance will be displayed only where the absorbance of the two cycles differs. Notice this looks very similar to continuum correction diagrammatically, but it is very important to note that here we are using the same source with the same spectral resolution when measuring the AA plus BG and BG components. This enables Zeeman to accurately measure structured background, which is not the case for continuum. In summary, Zeeman correction is measured from a single source, eliminating any intensity matching and alignment issues with the same spectral resolution that can correct for higher levels of background, including that containing any structure such as molecular bands. From a technological viewpoint, Longitudinal Zeeman works in concert with transverse heating, which eliminates the coolants of the tube to enhance graphite furnace performance to the next level. However, it is very important to note at this point that full STPF compliance can be accomplished with either Zeeman or Continuum based on the sample matrix. With Zeeman background correction, the emission profile of the line source is identical for both AA and background measurements as previously mentioned. As a result, most complex structured background situations can be accurately corrected for with Zeeman background correction. This can be seen in the figure above, where background absorption due to the presence of aluminum in the graphite furnace determination of arsenic is completely compensated using Zeeman correction, but produces erroneously high results with continuum source background correction since the aluminum would represent structured background. Here is yet another more classic example where phosphate bands found in a fish tissue matrix are providing a potential source of structured background. Since the background component with continuum source is measured across the entire spectral bandpass, it is actually greater than the background occurring at the wavelength as measured with the primary source lamp, resulting in overcorrection or overcompensation of the net AA signal, causing it to drop below the baseline. With Zeeman correction, the use of a single source with the same spectral resolution accurately measures the BG component when the magnet is on in this case, eliminating the overcorrection problem and producing more accurate data. Now, let's take a look at the actual gas flows in the furnace area itself. The heated graphite is protected from air oxidation by the end windows and two separate streams of argon. An external gas flow surrounds the outside of the tube and acts as a protective or sheathing gas, and a separately controllable internal gas flow purges the inside of the tube, the flow of which is controlled by the furnace program. This idea of separate gas flows is a very important design consideration, providing the ability to stop the internal gas flow during atomization while still maintaining the full flow of the external gas to protect the tube. This helps to maximize sample residence time in the tube, increase the analytical signal, and extend tube life. In evaluating the possible gas options for the graphite furnace, argon is inert, relatively inexpensive, and used almost exclusively. However, there are other options. Nitrogen, for example, is inert and optically transparent, but does create a significant safety issue when temperatures exceed 2300 degrees, as indicated above. Oxygen or air charring as an alternate gas can be useful when the pyrolysis step of the sample causes a buildup of carbon on the tube platform that will significantly begin to alter the kinetics of heating. Note that you are limited in the maximum charring temperature or oxidation and degradation of the tube will begin to occur. Because of its potential applicability, let's take a much closer look at argon hydrogen as a mixed gas and its implementation in EPA method 200.9. EPA method 200.9 can be applicable to a wide variety of matrices and allows for the use of a mixed digestion that includes hydrochloric acid, which can potentially speed up the overall analytical process by eliminating the need for separate digestions for graphite furnace. We know from a historical perspective that chlorides cause very volatile forms for elements such as cadmium, thallium, lead, and silver that create analytical issues. Knowing that, a method must be devised to account for the HCl, and 200.9 was designed for this. Notice that we must use a single modifier of palladium magnitrate and argon hydrogen as a mixed gas. Next, we will discover why this is absolutely necessary. Here we see the rather dramatic effect of chlorides as introduced in varying amounts of 2% hydrochloric acid with a traditional furnace program in use with palladium and magnitrate as a mixed modifier. It can be readily seen that we are losing significant amounts of lead and thallium in particular before we even reach the atomization step. This will clearly produce inaccurate, low-biased sample data. However, if we perform the same experiment using the modifier with argon hydrogen as a mixed gas, notice the effect is significantly reduced or eliminated by this combination. So how does this work? In essence, palladium in a reduced atmosphere, as created by the hydrogen in the mixed gas, becomes a more effective analyte sponge, if you will, for the analyte, and the hydrogen combines with the chloride, moving it during the pyrolysis step. The critical takeaway is that you must use palladium magnitrate as the modifier and argon hydrogens as a mixed alternate gas. In that case, what would a 200.9 furnace program actually look like? Let's start with the HGA design. We will always perform drying and charring with the mixed gas, but need to purge the furnace and switch back to just argon for atomization and cleanout. In this design, we use the pre-atomization cooldown step to perform this function. For an HGA design system, the pre-atomization cooldown step is part of the default furnace program, and it creates a slightly longer zone of isothermality along the length of the tube measured from the center when atomizing from 20 degrees compared to the pyrolysis step, where a heat transfer from the outer tube to the platform has already begun. This does not eliminate the cool end phenomena. It simply attempts to make the zone smaller with the cooldown step added. Regardless, it is imperative that atomization and cleanout occur in an argon atmosphere only to prevent the formation of hydrides in the furnace for those applicable elements and prevent unwanted tube degradation. This is what the program in a THGA furnace would look like. Since this design with its transverse heating already produces an isothermal condition along the entire tube length, the pre-atomization step is not required and therefore removed. In this case, we add a dummy char step with the same temperature as step 3 with a 20-second hold time designed to replace the mixed gas with just argon for atomization and cleanout for the same reasons mentioned on the previous slide. Since modifying a default furnace program using just argon to argon hydrogen as an alternate gas for 200.9 is quite easy, and considering the implications for the benefit of pre-reduced palladium, I believe the analytical benefits may extend well beyond those matrices specifically known to contain chlorides, with the ultimate goal of reducing background and improving data quality. As a result, we might consider the combination of palladium magnesium nitrate as a mixed modifier with argon hydrogen as a universal modifier. So there you have it. To review, perform the required maintenance, setup, alignment, and optimization of the system to verify performance before calibrating. Incorporate the STPF concept routinely to produce rugged furnace programs and maximize your data quality. And lastly, remember, EPA method 200.9 implementation must include palladium magnitrate with argon hydrogen with no exceptions to work successfully. We thank you for your time in attending this presentation and hope you found the information valuable. And now I believe it's time for some questions.